Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today we have Rob Bramley from CSIRO to talk to us about the Future Farm project.
Thanks, Nicole. So what I want to do today is to make some introductory comments about Future Farm as a lead into a series of videos that you'll see from different members of the Future Farm team. They'll be providing videos to SPAA subsequently. I guess everybody's familiar with the idea of the 4 R's, the notion of putting the right rate of the right product in the right place at the right time. But I think we sometimes should be asking ourselves whether 4 R's are enough. So for example, do we have the right equipment? Are we pursuing the right objective, whether that be in terms of yield or quality or both? And how do we know what right is? Do we have the right data? Does this data have to just come from on farm? Are we making use of it at the right scale? How do we think about growers' risk in implementing the 4 R's? And would some on-farm trials be useful to assist with getting things right? And I guess that fundamentally Future Farm is a project that seeks to tackle some or all of these questions in different combination. And in particular, the project aims to re-examine and improve the way in which soil and crop sensors and data from elsewhere are used to inform decisions about input management. And also we're particularly interested in automating the process from data acquisition through its analysis to the formulation and implementation of decision options. The initial exemplar use case is nitrogen fertiliser management in wheat, largely because nitrogen fertiliser accounts for such a significant proportion of the input costs of production. But Future Farm's not a nitrogen project per se, it's more about the use of the sensors and the automation. And contrary to popular rumour, it's not about robotics. I guess the other thing that's important to say about Future Farm is that it's a collaborative and co-funded effort involving input from CSIRO, the Universities of Sydney, Southern Queensland, Agriculture Victoria, the Queensland University of Technology and the GRDC. Now, if we think about a typical agronomic decision, such as a decision as to whether or not to apply fertiliser, we might typically use our mechanistic knowledge to identify a series of agronomic parameters, and measurements of these are coupled together in some sort of decision support system to help us arrive at our decision. But since the advent of various ag technologies and precision agriculture, we now have a range of sensors that we use to help make these measurements of agronomic parameters. And whereas some of these sensors are easy to calibrate, things like yield monitors or soil pH or moisture sensors, some of the other ones are not so easy to calibrate. And I guess a lot of effort has been put into generating calibrations of these various sensors to make measurements of these agronomic parameters. But the question arises as to whether or not that's the most sensible approach. Meanwhile, some service providers are using some of these sensors just as singular inputs to a decision and trying to generate recommendations about decisions without considering whether or not more information would be desirable. And in Future Farm, one of the underpinning ideas is that most agronomic decisions are really multivariate issues. So they need to factor in multiple inputs. So in other words, multiple soil or crop sensors. We might draw on data that's historical from on-farm or broader publicly available data, such as weather data or soil data, and indeed crop models. And a second important underpinning idea for Future Farm is that some on-farm experimentation could make a key contribution in making our decision much more site-specific, which is obviously what we want to do in a precision agriculture context. So instead of drawing on or following this kind of pathway to a digital decision, in Future Farm, what we're doing instead is saying, well, we'll use our mechanistic model to choose some appropriate sensors. And the ones that are easy to calibrate, we'll continue to put effort into calibrating. But the ones that are more difficult to calibrate, we won't worry so much about calibration, and we'll just use the data that they generate, and we'll combine all of that in some sort of data-driven model that's further informed by some on-farm experimentation and also data acquired from off-farm sources and perhaps at a scale much broader than the whole farm, and use those various different data sources to derive a sensor-based, data-driven and targeted decision. And what you'll see in the following series of videos is various members of the Future Farm project team talking about research that they're doing that addresses particular parts of this framework in order to enable us to come to this sensor-based targeted decision. So I'll leave it at that. Hopefully you gain some value from this series of videos and ultimately gain some value from the Future Farm project overall. So thanks very much.
Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today, we have Andre Colasso from CSIRO to continue the Future Farm series.
Thanks, Nicole. Hi, everyone. I'm here to talk to you about Future Farm, and more specifically about our field program and the scientific approaches we're following for the development of digitally based decision support systems for nitrogen in cereal crops. So Future Farm established a network of on-farm trials since 2018 in collaboration with farmers. And as you can see, our trials are spread across Australia with the CSIRO team looking after the Western and the South Australian trials. And we have also partners with Agriculture Victoria and University of Sydney looking after the eastern sites. I'm more particularly involved in the South Australian trials. Our trials are based on large-scale, spatially distributed experimental designs, which are implemented and monitored using precision agriculture tools, such as control traffic, variable rate equipment, and yield monitoring, for example. And this map here illustrates one of our trials where we have a nitrogen-rich strip and nitrogen-minus plots spread across the paddock to create a range of nitrogen availability for the crop. And as you can see, these strips are crossing the different soil zones in the paddock, which were previously mapped based on digital soil surveys. We monitored these trials throughout the season using remote and proximal crop sensing. We also have soil moisture sensors spread across the paddock. And we're collecting plant and soil samples at these target sampling locations for sensor calibration. So we can build this spatial database with the different information layers across the paddock. So the overall idea is that these trials are designed to explore the natural variability found in the field, so we can make observations of crop response to nitrogen and collect information across a range of crop and soil conditions within each trial. So the different research groups in Future Farm are exploring a range of approaches for a sensor-based nitrogen decision. And at the moment, I'm particularly involved in 3 approaches. So the first one, we're aiming to obtain a response function based on the sensor value and the response and the on-farm experimentation. And as you can see here in this example, the mid-season NDVI response was quite similar with the final crop response in terms of nitrogen, and they're both indicating a similar optimum nitrogen level. So we're now exploring the use of soil moisture information to increase the reliability of this approach across different low rainfall, rainfall environments. And The second approach is looking at nitrogen dilution and how the critical nitrogen level varies depending on crop biomass. So we're looking into different sensors to predict both crop biomass and nitrogen concentration. And we're looking into LiDAR and reflectance sensors for the prediction of those crop features. So we can use this framework here for a nitrogen decision. And finally, we're developing also non-mechanistic sensor-based algorithms that put together a range of information from a range of sources, including sensors and off-farm data as well, and on-farm experimentation. So we put all this together and calibrate it directly against an optimal nitrogen decision. So I'm more particularly involved in the on-farm data, such as the sensing data and the on-farm experimentation, and other colleagues are looking into the off-farm data, such as weather data and remote sensing information at the regional level as well. So we believe that by exploring a range of options and approaches, we'll be better positioned to deliver value to farmers that might have different data availability and different risk profiles in different farm operation and production systems as well. So watch this space to find more about our results, and thank you for watching.
Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today, we have Mario Fajardo to continue the Future Farm series. He's from the University of Sydney.
Thank you, Nicole. So, as some of you have heard on the previous presentations, I'm part of this multi-institutional project called Future Farm, and I'm going to talk specifically about bringing on-farm data to bear on nitrogen decisions. So, as a background, just to revise what the Future Farm project is, it's a program of field trials across the 3 regions of the GRDC to evaluate a combination of different proximal sensing technologies, historical on-farm data, historical data in general from the farms, and public available off-farm data, rather satellite information, rather proximal sensing methods, etc., and other various data fusion methods to better predict the response of nitrogen in the different agroecological regions of Australia. So that's the main background of the project. I'm just going to focus in a particular thing, which is bringing off-farm information, more specifically satellite information. As many of you know, we use NDVI for representing or characterizing the plant status. It's a widely known index, and we have seen that it has a high relation with the nitrogen and with the plants. The problem is that NDVI is just a qualitative measure of vegetation density, and it's not a quantitative measure of how much vegetation is present. It's just an index. Instead of leaf area index, tells you how much leaves you have per square meter. So we have this satellite made by NASA, which offers a worldwide product every 4 days. And we see that for example, in the Amazon, we have a lot of leaves, and then in the center of Australia, we have less leaves. So it's a good proxy of how much plants we have. But for precision agriculture, we have a little problem that the product it's just 2 cores. So for example, in this trial in South Australia, it's part of our core sites. We can't use it for precision agriculture. So what are we doing is taking the best of different constellations of satellites publicly available for the community. We take the MODIS, the product, which has a low spatial resolution of 500 meters, as we saw, but it has a high temporal resolution. It's every 4 days worldwide. And we take, on the other hand, the Sentinel constellation, it's offered by the European Space Agency, which doesn't offer a leaf area index product, but it has a high spatial resolution of 10 meters. And how we fusion those together via a machine learning approach that, of course, I won't present in detail now. So now I'm going to show you one practical example of what are we doing. This is a publicly available data set in a publicly available software as well. So we see that in this trial, our input, this will be the MODIS leaf area index, which has a resolution that, of course, is not useful for us. However, if we see our predictions, we can see that these lines over here are N-rich strips, and the other small ones are the N- strips, and we can see that if we predict in time, we have a response that is useful for predicting our plant status in time. So we see these are leaf area index predictions using both satellites constellations. So hopefully we will present these results in the future and in the real. Otherwise, it will be via Zoom and yes. So if you have any questions, here are my contact details. I'm part of the Precision Agriculture Laboratory of the University of Sydney, and I'm working in the Future Farm project with all these institutions. And yes, thank you very much, and see you soon.
Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today, we have Alex Clancy from Agriculture Victoria to continue with our Future Farm series.
Thanks, Nicole. So I guess just to start off with, I'm Alex Clancy and I'm a research scientist with Agriculture Victoria based in Horsham, working as part of the broader national team on the Future Farm project. So just to reiterate one more time, the Future Farm project is a program of field trials across 3 GRDC regions to evaluate the combination of proximal sensing technologies, historical on-farm data, publicly available off-farm data, and data fusion methods to better predict the response to applied N in different agroecological zones across Australia. In this talk, however, I'll be giving a little more of an outline of some of the work that's been completed around this aspect of the trials, being the evaluation of proximal sensing technologies, including a comparison of vegetation indices. So in Victoria, our site was located in the Southern Mallee, but apart from the geographical change, the trial design was similar to the other states, where we had both an N-rich strip and a 0N strip, and finally a paddock strip, which represented the blanket N applications of the remainder of the grower's paddock. And over the past 3 winter seasons, we have monitored the crop for a series of agronomic traits and also made regular measurements with active sensors like the crop circle and with passive sensors like satellite and hyperspecs. So passive and active sensors are the main tools we and industry would use to acquire crop vegetation indices, and I guess the most commonly used would be NDVI. So when we talk about active and passive sensors, I guess what we're referring to is sensors that either provide their own lighting for the target, which is an active sensor, or those that have their own light, or those that are using a light source from the sun's illumination, which would be our passive sensors. So this critical difference in design means that each sensor actually operates best under certain conditions and on certain platforms. As an example, crop circles are an active sensor, which can provide calibrated fine scale index values even on a cloudy day. However, they need to be run on fairly tight spots across a whole paddock and fairly close to the canopy as well. Alternatively, we have something like Sentinel-2, which can provide whole paddock data within a few minutes. but is subject to having clear sky conditions only on certain days, and is also known to saturate at high reflectance. And so while both these systems are able to provide NDVI values, I guess the message here is that these two systems can actually provide very different results in conjunction with being available to a grower or an advisor at very different times. So when we look at the Victorian site for the Future Farm project, we can see how, as an example, NDVI values can change depending on the sensor platform. And so here we have the 26th of September back in 2018, where we captured reflectance values using a crop circle unit on the same day as we had a flyover from Sentinel-2. And we got that comparative reflectance from space. So ignoring the changes in scale and how the two are collected, we can see actually for the most part that the trends between the two systems are very similar. But when we take a closer look at the relationship between the two, we see something like this, where we actually have a non-linear relationship between the two. And that's as a result of the satellite data saturating at high reflectance, while the crop circle, being the active optical, is more or less holding course. So one thing that is often done to deal with this saturation from Sentinel imagery is to substitute NDVI to NDRE. And so NDRE uses a slightly different area of the plant spectrum, using what's called the red edge instead of the visible red used in the NDVI equation. The issue here is while both can correlate quite nicely, they are actually better indicators of different things. So NDVI is best correlated with biomass, but this trend does tend to weaken as the season progresses and crop biomass increases. Alternatively, NDRE is a much better indicator of N concentration, but less applicable to biomass. So another way we can overcome some of the limitations of the one-off measure of NDVI and NDRE is to look at changes over time. This not only helps us with the understanding of crop growth trends, but enhances our ability to predict biomass without running into too many issues with saturation when we use, as an example, NDVI as a summed value over time. And so ultimately by doing so, we can improve the reliability of data being used as an input for N prediction and application. So thank you very much and take care, everyone.
Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today, we have Steve and Leo from Queensland University of Technology to continue with the Future Farm series.
Great, thanks Nicole. Hi everybody, my name is Stephen Leo and I'm a PhD student at QT in Brisbane. Today I will be further adding to the previous Future Farm videos by talking about the cotton aspect of this overall project and specifically about predicting in-season cotton nitrogen status using Sentinel-2. So the goal of the cotton aspect of the Future Farm project is very similar to the grains by using on-farm and off-farm data sources and data fusion to be able to better predict nitrogen response and therefore improve overall nitrogen use efficiency. So this component of the Future Farm project was funded by the GRDC. So currently most cotton systems are overloaded with nitrogen, largely due to the recent low rainfall seasons, but also due to cotton soil's high mineralization potential. In addition to this, pre-plant nitrogen applications are prone to high nitrogen losses due to the high clay content of these soils and denitrification, where up to 50% of applied nitrogen can be lost. Alternatively, in-season nitrogen applications can be more efficient and profitable for the grower. In-season nitrogen application rates are typically based on petiole nitrate and leaf nitrogen samples, ideally collected multiple times throughout the season. However, these samples are typically bulked, therefore neglecting the spatial variability within fields, and ultimately a uniform nitrogen rate is applied. So for this particular case study, we evaluated the potential of Sentinel-2 vegetation indices, specifically NDVI and NDRE, to be able to predict these in-season parameters. So to do this, we imposed 4 nitrogen rates across 2 field sites, and then within each field site, we had 2 management zones where they ranged in soil properties. And then we collected petiole nitrate throughout the season at squaring and flowering. And in addition to this, we collected leaf nitrogen at the same time, in addition to bulb fill and maturity. So firstly, to test the prediction accuracy of Sentinel-2, we used half of the data we collected to train a model, and then the remaining half to test its accuracy. So in regards to leaf nitrogen, we saw promising results using the daily cumulative of NDRE from planting, which provided a Linz concordance correlation coefficient of 0.89. So the closer this Linz concordance correlation coefficient, or LCCC, is to 1, the better the fit is between observed and predicted values. In terms of petiole nitrate, we see some very promising results here, even though we did have a smaller data set, by achieving a LCCC of 0.86 using the cumulative NDVI in this case. Another aspect we explored, which is a concern from a remote sensing standpoint, is the inaccurate representation of nitrogen status due to cotton's ability to be able to transport nitrogen from the older lower leaves to the higher younger leaves within the canopy. So to test this, we assessed leaf nitrogen concentrations at the top and the bottom of the canopy and plotted these against Sentinel-2 vegetation indices. So the relationship that we saw between the leaf nitrogen at the top of the canopy and the cumulative NDRE was quite moderate to strong, with an R-squared of 0.62. However, when we did the same relationship between the bottom of the canopy, we do get a slightly lower relationship, but still see some promising results there to be able to detect that nitrogen stress lower in the canopy. Lastly, if you have any questions or comments about our research or this particular video, I would love to hear them, so please don't hesitate to contact me with the details displayed here. Thank you for listening.
Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today, we have Jonathan Ricchetti from CSIRO to continue with the Future Farm series.
Thank you, Nicole. One aspect that we're looking with Future Farm is how to integrate data in crop modeling. As you ought to know, the Future Farm is a collaborative project. If you missed that, look back at this SPAA video series for the complete picture. So what's the plan? What you're looking at? We know that crop models can simulate the status of a crop, but we need to be sure that they are doing the right thing, which is not a simple task. To do so, we need to calibrate the model, and that requires data. Previously, these data were acquired by sampling, but now there are new streams of data that were not available before. So can we integrate such data in the models to drive a decision? If so, how can we do that? The very fundamental of precision agriculture is the recognition that each part of the field is different, and its differences should be considered when decision making. Different soils means different plant available water capacity. That means different growing conditions that reflect in the different yields, and so different nutrient requirements. In this case, nitrogen. Models need to be calibrated to each of these differences, but how can we calibrate a model for each point of the paddock? This is what we're looking at. At this paddock, we have different nitrogen treatments and different soils. A minor strip with a low N application, a farmer strip, that is whatever the farmer decided, and a rich strip, that's the double of the farmer's decision. With sample points across the experiment, and in each point, we want to calibrate the model so we can assess the plant needs. For example, point 1, it's a sand earth, while point 21, it's a sandy duplex with sand on top and higher clay content below. How can we inform the model about what is going on down under without digging? The concept here is to use the crop above. As said, with different soil different growing behavior, and so different biomass and different leaf area index, LAI for short. We've measured the normalized difference vegetation index, and using the Beer-Lambert law of light extinction, we determined the crop leaf area index. Then, using the Nelder-Med optimization algorithm, the LAI was used to calibrate different soil parameters in each point. So the differences in the soil are now also in the model. Each point now has a calibrated model with different soils that matched the LAI, with a LAI mean error of 0.01, and with the calibrated model, the yield mean error was 43 kilograms per hectare and a standard deviation of around 450 kilograms per hectare. Now that we have a calibrated model that reflects what's going on in the paddock. So by measuring LAI with the sensor in each point, we can use the optimization algorithm to tell the model what has happened, and so adjust the soil parameters to reflect the reality. Once improved the modeling by calibrating it with the new streams of data, we can now use it to simulate some scenarios. That is, now that we have integrated the LAI into the calibration framework, we can start building the decision framework with the calibrated model. So that means we can explore future weather scenarios and build a probabilistic nitrogen decision mid-season. And for each of the points, so we're taking into consideration the differences around the paddock. Soon we'll have more updates on that. As a quick addition, drones and satellite can be explored for more detailed resolution. Thank you for watching. Any doubts, please let me know.
Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today, we have Alison McCarthy from the Centre of Agriculture Engineering within the University of Southern Queensland to continue with our Future Farm series.
Well, thanks, Nicole, and thanks everyone for joining us for the next video in this series. I'm a mechatronic engineer at the University of Southern Queensland, and today my topic will be on our team's sub-project within the GRDC funded Future Farm project, specifically on using machine vision as an alternative approach to nitrogen decision making. And this project focuses on improving sensing and control decisions for site-specific nitrogen application within the season. So typical existing automated sensing for making nitrogen decisions is currently often based on remote sensing approaches, for example, vegetation indices like NDVI and NDRE, and these are sensed using sensors like those pictured here, like a green seeker or crop circle, which is mounted on a tractor. However, from existing research from other teams within the project and also in the literature, this can have an inconsistent relationship with nitrogen status. Often these vegetation indices are an indicator of crop cover, and so because of this inconsistency, this indicates that additional data or processing is required to be able to use this information to make nitrogen decisions. Another source of data that can be incorporated into the nitrogen decision, things like information about the underlying variability over the field. So things like sowing density, soil properties like drained upper limit, and also soil moisture status over the field. Now, another approach that we are looking at incorporating into nitrogen decisions is actually machine vision, which can automatically extract information about the crop. And we envisage this machine vision data can be collected using a camera that could be installed next to a green seeker or crop circle on a tractor. And what this will let us do is collect additional crop feature information that can indicate the nitrogen status of the crop. This can include things like the height of the plant, the tiller count, other indicators about the size of the crop, like canopy cover, as well as the color of the crop, and also the reflectance in other spectra, which can be collected using a multispectral camera. Here I've just got an example of some machine vision algorithms that have been reported in the literature, which can actually extract the number of tillers on a grain crop. And so we have conducted some initial data collection at some plots set up within our ag plot here at the University of Southern Queensland, and used this for data collection over 2 seasons, where we collected machine vision data, crop features, as well as NDVI and NDRE and underlying variability information, and linked these with estimated soil nitrate and soil ammonium, and incorporated this into a nitrogen status algorithm. And from this, we found that using remote sensing and underlying variability information, we're getting accuracies for estimating nitrogen status of about 66%, specifically for soil nitrogen, and up to about 47% for soil ammonium nitrogen. When we use machine vision information with the underlying variability over the plots, we found actually improved accuracy over the remote sensing approach. So we're getting up to 77% accuracy in estimating the soil nitrate nitrogen, and up to 72% accuracy in estimating the soil ammonium nitrate. So next steps in this research, first of all, to verify these results and these nitrogen status algorithms across more sites. We've actually collected data in this year's grain season across all of the Future Farm core sites. And so we'll be able to compare the performance that we got with our trials here at the university with those sites nationally, and also evaluate and refine our machine vision system that can extract these crop features. I'd like to acknowledge the funding for this research from GRDC and also feedback that we got on our research from our project collaborators. And also like to thank our Centre for Crop Health within the university for managing our trial. Here we've also got our contact details if you'd like further information on our project. Thank you.
Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today, we have Anand Pahula from the Centre of Agricultural Engineering within the University of Southern Queensland to continue with the Future Farm series.
Thank you, Nicole. In continuation to the video series 3 Minutes with the SPAA, today my topic is bringing it all together with a common sensor platform. To give you an overview of the Future Farm, once again, just recap of the series. Future Farm is funded by GRDC, a multi-agency initiative where CSIRO, University of Sydney, Ag Victoria, Queensland University of Technology, along with University of Southern Queensland, all together working in this particular research project. The overall objective of the project is to collect the data from various sensors, soil and crop sensors, vision sensors, combined with on-farm data and off-farm data to inform a data-driven automatic decision for a potential real-time nitrogen management. So coming to common sensor platform, it consists of 4 stages. In stage 1, the hardware and software of the common sensor platform is being developed, which is capable of interfacing a range of sensors, collect real-time data. Data is being synchronized and stored locally on common sensor platform. In stage 2, the data that is being collected on stage 1 is pre-processed on board on the common sensor platform. So the purpose of this stage 2 is the data that is being collected, for example, like image data and LiDAR data is very huge. We cannot store all the data on the cloud. So the pre-processed data, the features extracted from these data will be sent to the cloud for algorithm development, for precision map development. In stage 3, the hardware will be upgraded for variable rate application for the attached vehicles. Algorithms runs on the server, convert the data into a precision map and send back to the common sensor platform, which will be used for variable rate treatment. The final stage is a complete autonomous real-time variable rate application system. As I said, in stage 1, the common sensor platform is being developed. The developed CSP hardware is portable, durable, weatherproof, and easy to plug and play. Some images showing the hardware schematic. Connections are presented here for easy understanding. The software is again developed by robotic operating system on Ubuntu platform. The programming language used is Python, and PyQt is used for graphical user interface. The node graph shows how the data is being collected. I'm not going into the details at this moment. So the software is very user friendly. Just double click on the USQ CSP icon. It pop-ups the form, which has 3 buttons: verify connections, start data, stop data. Just click on verify connection, shows the number of sensors that are attached to the common sensor platform. Start data will collect the data, stop data will stop the data. As you see in the picture, Phenom Green Seeker dual EM camera is being connected and collecting the data. So this picture shows how the common sensor platform can be mounted on a sprayer. The top picture shows a camera Phenom Green Seeker that are being connected with the common sensor platform. The bottom picture explains dual EM. Collecting the common data from the common sensor platform can be done in 3 methods. One method is directly from the display screen, which comes with the common sensor platform. The remote access can be done by using the laptop with an internet access, or without an internet access by using an Ethernet card. But the best option is utilizing the screen on the common sensor platform. We are trying to take this particular screen into the tractor cab so that it is easy to operate. So this is about common sensor platform. In future steps, we are trying to integrate the common sensor platform with a liquid fertilizer for variable rate application. That's all about common sensor platform. If you have any questions, feel free to contact me on my contact details. Thank you.
Welcome to 3 Minutes With, where we meet researchers and their precision agriculture projects. Today, we have Mario Fajardo from the University of Sydney Precision Ag Lab to continue with the Future Farm series.
Hello, Nicole. Thank you very much. Today, I'm going to show you some of, a snapshot of the work that we're doing in accessing useful publicly available datasets to assist decision-making on farm. And this particular work, it was published a few days ago. The name is Within Farm with Yield Forecasting by incorporating off-farm information. When I'm saying off-farm information, I'm referring to all these freely available datasets that are worldwide. In this particular case, we use a set of remote sensing imagery and some climate variables and some soil attributes and some terrain attributes. So the soil attributes were obtained in the Soil and Landscape Grid of Australia. This is a free service that, there are different soil attributes that are freely available for the audience. This is the web page where you can obtain the dataset. And the web platform that we use was Earth Engine. Also, you have the web page in there. And even though we didn't use rainfall in this research, You can also obtain rainfall information through the Bureau of Meteorology, and you have the web page in there, and you can access a daily gridded rainfall for the whole Australia. So briefly, the data sets were 6 data sets, and if we go from up to the bottom, we have increasing spatial resolution, and from left to right, increasing data quantity. So in the first data sets, we have in the upper part, we have Landsat imagery. So we have with harvest information from the paddocks, plus Landsat imagery, plus the soil attributes, plus terrain attributes. And in the lower part, we have, instead of Landsat imagery, we have Sentinel imagery, which is a higher resolution imagery. And in the second group of data sets, we have the same data sets plus private proximal soil sensing service. So this was acquired by the owners of the farms. And in the third group of data sets, and this is the most important part, we have just freely available data. This is remote sensing, but from neighboring paddocks. And we found out that even though the proximal soil sensings were, they had really good results in forecasting the wheat yield, we have the extra information from surrounding paddocks provided an even better prediction. And this is some of the results that we found. This is a 3 months ahead harvest or before harvest prediction of wheat yield, just using information from outside the paddocks and freely available. So again, I thank you for watching this, and these are my details, and I'm working in the Future Farm project, and I'm part of the University of Sydney. Thank you very much.